Hi, I'm Jignyasa from FindMyTest team, and I'll be conducting lectures on Geomatics Engineering, Part A, that is the common part. And I'll begin with the remote sensing lectures first, then move on to GNSS, and then GIS. And then we'll do this engineering mathematics. Okay, so let's start with the basic concept of remote sensing. So basically, this is the most used definition of remote sensing. Any information that we gain remotely of an object is remote sensing. Thus, the object should not be in contact with the target, not in contact with the target under investigation. The most used common example is our eye, or sensing whether a vessel is hot vessel. So basically, any information that we gain remotely of an object is remote sensing. So let's move on to the basic components of remote sensing. This is the image that I took from Kiefer book, which is a well-known book of remote sensing, and I would suggest you to read it. So it gives a process. It is giving the process from data acquisition to data analysis. So this part up till E is data acquisition, and F, G, H, I is all data analysis that will run in digital image processing. So in here, the first step, I'll explain you these steps first in the next slide, and then we'll move on to digital image processing in the later section. Okay, so this is the basic components of remote sensing. Components of remote sensing. A is the energy or source of illumination, that is here. Usually it is the sun. Then comes B, that is radiation and atmosphere. Then comes C, that is the interaction with the target. Then comes D, that is recording of the sensor. And then comes transmission, reception, and processing. And then the image interpretation and analysis, and finally the application. So we learn these one by one. And hopefully when we finish this all seven, then our basics of remote sensing will be covered entirely. Okay, so let's move on with energy source and illumination. So I'll just explain this process in short. So A is the source of energy, that is the sun. Sun emits electromagnetic radiation, that is EMR. It travels in the form of waves or particle form through the atmosphere. B is the atmosphere. Here it interacts with the atmosphere, and the waves may not be in the same form as it was in the emitted form. That it may get scattered due to the atmosphere or the particles in the atmosphere, so it may not remain in the same form. So it hits the target, that is C, that is our Earth surface. So some of the energy gets reflected back, some of the energy gets emitted, some of the energy gets transmitted and absorbed. So this emitted energy or the reflected energy, here we see this is B. This is the reflected energy. So this is again in the form of electromagnetic radiation. So this radiation is actually sensed by the sensor on the satellite. So here is the sensor that senses this electromagnetic energy, that is the reflective electromagnetic energy uh, uh, emitted by the Earth or reflected by the Earth's surface. So this sensed energy is then converted into DN values, digital numbers, or a numeric value, and this value is sent to the ground station. This is the ground station. This is sent to the ground station or another satellite, and this is again then converted to images, and any application is made based on these images. So remember this, that when the sun is the source of energy, it emits in the form of electromagnetic radiation that hits the Earth's surface, and then it is reflected back or absorbed, and this absorbed energy is again emitted by the Earth's surface, that is sensed with satellite. So the satellite senses both emitted and reflective energy. Then another thing is, one more remote sensing technique is the sensor of the satellite itself creates the electromagnetic radiation. So this is the electromagnetic radiation by the satellite. So this is sent to the earth and this is reflected back. So this method is called as active remote sensing, and this is called as passive remote sensing, where the sun is the source. We'll learn about this more in the next slide. Just remember this process, how exactly remote sensing works. Let's move on to the active and passive remote sensing. First component of remote sensing is the energy source. Based on the energy source, remote sensing can be divided into two parts, that is active remote sensing and passive remote sensing. So in passive remote sensing, the sun is the source of energy. It is a natural source of energy. Uh, in active remote sensing, the satellite is a source of energy. That is, it is an artificial source of energy. Passive remote sensing can be either reflective or emissive. While active remote sensing is always reflective. That is, it measures only the reflected electromagnetic radiation from the Earth's surface. So when the electromagnetic Earth surface enters the Earth's atmosphere and hits the target, consider this is the Earth's surface, that is the target, the energy gets either reflected, absorbed, or transmitted to the Earth's surface. So basically, when we measure reflective this reflective energy is measured by the artificial sensor, that is in active remote sensing. In passive remote sensing, both the reflective as well as the emissive energy is measured. So once the Earth's surface absorbs the heat or the electromagnetic radiation, to maintain the heat budget of the Earth, it again emits this energy after some time. This emitted energy is measured in passive remote sensing. So this is the emitted energy. And so, sorry. This is the emitted. So this is the basic difference between passive and active remote sensing. You just need to remember that in passive remote sensing, the sun is the natural source of energy. Uh, Sun is the source of energy, that is a natural source. While in active remote sensing, the satellite itself generates the electromagnetic radiation, and then the reflected electromagnetic radiation is measured by the sensor. Thus, it is an artificial source of energy. While this measures both reflective and emissive energy, this only measures the reflective energy. So earlier I used the term electromagnetic radiation, which is EMR in short. So we have learned this in physics in school days, that what is electromagnetic radiation. So it is basically the electric and magnetic field oscillating perpendicular to each other in the direction perpendicular to both. It travels at the speed of light, that is 3 into 10 raised to 8 meters per second. And the waves are harmonic as well as in the sinusoid. That is sine waves in the sinusoidal form. So this is the image of an electromagnetic wave. This is the electric field oscillating in this direction, y direction. This is the magnetic field oscillating perpendicular to the electric field, and both are traveling in this direction. That is perpendicular to both electric as well as magnetic field. So we'll discuss electromagnetic spectrum now. After this, you can revise this electromagnetic radiation concept from your physics lessons. It is a basic concept of remote sensing and a basic concept of physics. Let's move on to electromagnetic spectrum. That is a major part of remote sensing. Before starting with electromagnetic radiation, I would like to tell you about a basic concepts of waves. That is wavelength. So what is a wavelength? Okay, it is the distance traveled by a wave in one oscillation. This is the crest of the wave. This is the trough. And wavelength is the distance this distance, that is one oscillation. It can also be this distance, the same distance. So that is the wavelength of the wave. Next is the frequency. Frequency is the number of oscillations. Number of oscillations. Oh, sorry. It is the number of oscillations of a wave per second or per unit of time. Per unit of time. As we are doing it for EMR, it would be number of wavelengths per second. So that is basically frequency and wavelength. So these two concepts you should know about a wave, which we actually learned in physics before. So the next thing is, one second. Next is finding the relation between these two things. So we know the formula, that is C is equal to lambda into nu. But this is wavelength and this is frequency. So C is speed of light. C is equal to 3 into 10 raised to 8 meters per second. So based on this equation, this is a very important equation. Uh, and based on this equation, we can say that wavelength is inversely proportional to frequency. So these two formulas are very important. Questions are asked based on this, mostly application-based questions. So remember this: as C is constant, wavelength is inversely proportional to frequency. So as wavelength would increase, as lambda increases, frequency would be lower. So these concepts are very important. Just remember these. Another thing is one more relation that I would like to point out is the what we learned in physics before. That is, oh, one second. That is wave theory and particle theory. So what does wave theory says? That if light travels, that wave theory has quantified energy is equal to hc upon lambda. So this is basically the wave theory stating that energy of the wave is dependent on the speed and its wavelength. Particle theory suggests that light travels in the form of particles, that is discrete particles, which we call as photons or quanta. Wave theory suggests that light travels in the form of a wave. Both of them come down to this formula, that is q is equal to hc upon lambda. The unit becomes joule, as q is the energy of the particle or the energy of the wave. This can also be written as q is equal to uh, q is equal to h into nu. Nu here is frequency. So q is equal to h into nu. H is Planck's constant. Has the value 6.626 into 10 raised to minus 34 joule second are the units. Okay, so this is Planck's constant. Just do it like this. So these two formulas are again important. It shows a relation between energy and wavelength and energy and frequency. So I'll just revise one thing. Remember, this is wave theory and particle theory. Based on it, we have derived these equations. You can revise it. It was in our physics, in school level physics. So yes. So I'll tell in short. So as wavelength would increase, frequency would decrease. With higher wavelength comes less energy. This is one relation that you have to remember. Another would be the opposite of this, obviously. When wavelength decreases, frequency is higher, energy would be higher. Another thing, you can remember it by logic also. So if a wavelength is longer, that is a larger wavelength, obviously its frequency would be less as the wave is traveling a longer distance in a small unit of time. And we have learned also that more energetic the particle is, the higher frequency it would oscillate in a higher frequency if it's more energetic. This actually means that the energy is very low of the particle to travel, the wave to travel. And if the wavelength is lower, then the frequency would obviously be higher because the wave would be like this. And such waves have a higher energy. So it is basically logical to remember. It would be better if you remember it logically. So this is the relation. Questions have been asked on this. So I would suggest you to remember this. These are the basic concepts of a wave. So we'll move on to the next thing. So now that you know about what is a wave, we can learn about the electromagnetic spectrum. So this is the image that I took from Lillison and Kiefer book that I told you about earlier. So these are the type. See, so this is the entire electromagnetic spectrum that we see of the light, that is the emitted by the sun. The EMR emitted by the sun basically. So these are the cosmic rays that has the large, largest wavelength. Then comes the gamma rays. This is gamma. Sorry. Then come the X-rays. Then comes the ultraviolet rays. Then the visible spectrum. Then comes the near infrared, mid infrared, thermal infrared. Then the microwave, and then the television and radio waves. So what happens is that the sun emits all these radiations. I mean the radiations are at different wavelengths. So these enter the Earth's atmosphere. Amongst that, cosmic rays get not even enter the Earth's atmosphere. Gamma rays may enter, but they don't penetrate the entire atmosphere. X-rays also don't penetrate the entire atmosphere. Ultraviolet rays, UV rays, as we have known that they penetrate the atmosphere and are harmful for human beings. Then comes the visible spectrum. This is the spectrum which actually we can see. This is a small spectrum that we see, including the Vibgyor colors. Basically, this is V, I, V, G, Y, O, R in this form. And then comes the near infrared radiation from the sun. This is the mid infrared, thermal infrared. Thermal infrared is basically the thermal radiation that we see. This is the emitted energy of the earth is in this form, in this region, that is the thermal region. Then comes the microwave and then the radio waves. This is for television and radio. This is not used in remote sensing. These are not used in remote sensing, not this, not this. UV rays, not this. Only this patch that is from visible to the microwave is used in remote sensing. So the sun when emits the electromagnetic radiation, they come in all these wavelengths. So starting from the cosmic rays, gamma, X-ray, you have to remember this order because in GATE they may ask you the order also, that which is the largest wave, which has the largest wavelength, or arrange them in the order of the wavelengths, increasing order, decreasing order. So just remember that this is the order of the electromagnetic spectrum. The major part that we have to learn is this visible region, and visible region, it is very easy because with Gyar we know the colors of the rainbow. It is in the same order, right? So here it is violet, right? So on this side would be ultraviolet. So you should remember this. And as it is red, so this becomes infrared on this side. And this is the order of the visible spectrum. You can remember, you have to remember these wavelengths, which are also very important. Like, for example, just remember this RGB, B lies between zero point 0.4 to zero point 0.5, G lies from zero point 0.5 to zero point 0.6, R lies from zero point 0.6 to zero point 0.7. There is no specific as such differentiation that beyond this it would be blue, beyond this it would be green. So gate may not ask you questions regarding the specific exact number, but it's good to know the range on in between which it lies. So we cannot like say that after 10 it would be thermal infrared only. No, it may vary at some point. So it would ask a generalized question of the order or the units. You should remember the units. These are very important and confusing. Remember these units. It is usually given in micrometers, but sometimes they may confuse you by giving you millimeters or meters. Along with the wavelength, also you have to remember the frequencies of the waves. So cosmic rays would have the highest high frequency. Sorry, cosmic rays would have the high frequency as they have the lowest wavelength. The same way it goes. So the frequency would be decreasing in this order as the wavelength is increasing in this order. Wavelength is increasing. This is wavelength is increasing in this direction. So frequency would be increasing in this direction. So these are the basic concepts of electromagnetic spectrum. Another one thing that I have to tell you is when we say optical remote sensing, optical bands, or optical remote sensing, it basically includes visible region plus near infrared. Near infrared. So this is basically VNIR. This is the most commonly used bands for remote sensing, that is the visible bands RGB and the NIR band, that is near infrared band. So this is the electromagnetic spectrum. I will be briefing you more about this, elaborating more as we move forward. So this is the this is the basic of electromagnetic spectrum. You should, for now, you should remember what is wavelength, how the wavelength increases, what is the order of the electromagnetic spectrum, which has higher frequency, which has lower frequency, higher wavelength, lower wavelength, all these things you should remember. And remember this visible spectrum because questions are asked on this also. And don't get confused between the units. Okay, you can remember this. One second. Cosmic, this is beyond 10 raised to minus 8. All units are in micrometers. Then comes gamma. This lies around 10 raised to minus 6. Then comes X-rays, 10 raised to minus 4. Then comes UV rays. Rays lie between 10 raised to minus 1. Then comes blue. Blue lies 0.4 to 0.5. Then green 0.5 to 0.6. Then red 0.6 to 0.7. This is our visible spectrum. Then comes near infrared. This lies between 0.7 to 1.3. Then comes mid-infrared. This lies between 1.3 to 3. So basically, all this, all these are optical remote sensing. These bands are used for optical remote sensing. Then comes, and these two, that is the infrared bands, are not thermal bands. Remember this. Near infrared and mid infrared are not thermal bands. Here comes another band that is thermal. That is from 3 to 14. This generates the heat sensation. This detects the heat. So this is basically that you have to remember from thermal. And then comes the microwave that is beyond 14 micrometer to 1 mm. So this is micrometer. These all units are in micrometers. Remember the units. This I wanted to specify that this is optical remote sensing, blue, green, red, near infrared, mid infrared, up till 3. Then comes these two are not thermal bands. So remember this. And these are the basic ranges that you can remember. This is also given in the Listen and Kiefer book. So I would suggest you to read this and learn this by heart. Okay. Thank you. One more thing before ending this video, if you have any query, then please do WhatsApp to our team. Our FindMyTest team is available 24/7 on WhatsApp. Drop your message and on this number 950993958, and I would suggest please start attempting topic and subject wise tests of FindMyTest after watching the videos. Okay, thank you.